Hello there, math fans. Going to continue my quick discussion on cross products. I've already talked about the most important part of a cross product. If you didn't watch my previous video, watch that. It was this idea that the cross product gives you a vector that's perpendicular to the previous two. Here I have A, which is the blue vector, and B, which is the red vector. I'm taking their cross product. So I encourage you to figure out, is that cross product going to come towards us or away from us? Watch that previous video. But it's towards us. It's that purple vector coming up here. Notice it's really long. Does its length mean anything? For our purposes in this course, the length actually doesn't mean that much. There are some important applications of the length, and it has to do with the numbers involved. In this case, it's fairly simple to see, so I have this example. The length of this vector is the square root of 0 squared plus 0 squared plus 6 squared, so it's 6. It has an interpretation. And the interpretation is if you take those two vectors on the ground and form a parallelogram, the area of that parallelogram is the same as that length. It's surprising because it seems like those should be unrelated. The area is 6, the length is 6. Sometimes students complain and say, but the units for area would be like square feet. The units for length would be feet. Yes, I understand your complaint. I'm just telling you those two numbers are the same. There's nothing wrong with those numbers being the same. Yes, one would be area and one would be length. That's how we interpret that length. It tends to be really long for the most problems we deal with, because if both the lengths are greater than 1 and you multiply them together, you're going to get a length that's pretty big compared to both of them. Okay, this also works if they aren't, and it doesn't change if you go the other direction. It's still length 6. It just points the other way. And if you change and don't make them a right angle, it's also true. The area of that parallelogram right there and the length of this vector, notice it got a little shorter. In fact, the longest it can be is when they're a right angle between the first two. It gets shorter and shorter and shorter. There you go. So that's the connection between those two. So I'm going to take the rest of this time and try to explain a little bit why that's the case. It's not an easy explanation, but I'm going to try to show you a little bit and say some pieces, and it ties in with dot products. I'm going to say a little more than I normally would say in class, because I always skip over some of the arithmetic that happens in the textbook. Okay, so here we go. This is the fact where everything stems from. And we'll keep this example. Maybe I'll make it a little smaller. Put it over here. Over there. Okay, sorry for all the clicking. So ultimately, it's this fact. The reason it follows from this fact, so if this is true, and that's the fact that's hard to prove, this looks similar because we have this fact about dot products that says it's the magnitude of A times the magnitude of B times cosine of theta. I often tell students, I like this one better. That's why this one gets 10 stars. It's better to work with cosine because of the type of angles that come out of it. It's easier to compute. So there's a few reasons. But it really has to do with if you draw this parallelogram. This is the end of the proof, so I'm kind of going out of order. But the area of that parallelogram is the area of the base, which is what this is. That's the area of the base, times the height. And we can find the height by doing a little bit of trig. So we can say sine of theta is h over the length of b. So this right here is h. And that is the area of the parallelogram. If you aren't following, what I'm saying is that the area of this parallelogram is the area of A times h. And then I'm saying, by the way, h is the length of b times sine of theta. So that's why it's area of parallelogram. Now that still assumes that this connection is true. So now let's switch to that connection. Okay. So this is another one of our facts, not quite as important, but it does give you an ability to interpret this. Okay, the problem is every proof I've seen of this involves writing out the cross product and then finding its length. Why is that kind of a challenge? Because the cross product is a really big expression. Not only that, there's a problem that happens down the road a bit. But let's do a little bit of it. This is something I normally don't do in class. In fact, I don't think I've ever worked all the way through this. I'm hoping I can say a few things and glean some interest from this, because it's, like I said, not something I normally would do in class. So we're going to do this cross product, just so I can write down the formulas. Again, if you're a disciple of my method for doing this, you always do the following, because then you can hold the little bits in your head. So this is going to be A2B3 minus A3B2. This is going to be, so I crossed off the first column. Now I'm going to cross off the second one. A1B3, A3B1. And then lastly, cross off the last column, main diagonal, A1B2, A2B1. So the magnitude of that is the square. So usually what we do is the magnitude squared, but let's just write it. The magnitude of A cross B. And if somebody knows of a cleaner proof, please let me know. Oh, I'm squaring it. I'm a step ahead of myself. It is important, but we're going to do this squared plus this squared plus this squared. And this is why it's so bad. A3, B2. It's just not bad. I'm not afraid of a bunch of algebra. It's just big. In which case it becomes a little challenging to figure out how to put it together and how it's going to simplify. It does simplify, but it's kind of a non-obvious simplification. So what every proof I've seen of this expands this. It foils it out, it monkey faces it. So you're going to have all of these things squared. This is a good chance, I guess. You know, the positive of this is a chance for people that have trouble with expanding to think about it. So you're going to have this, and then you're going to have a bunch of middle terms. So let's take this a moment further. I do have some worked out stuff already, so I didn't want to make a mistake here, so I planned it out a slight bit. But mostly this is fresh thinking here. So we're going to do A2 squared, B3 squared. And then we're going to have this middle term. And I'm going to, in a moment, try to clean a few things up. And I'm just kind of thinking about it as I write this. Yeah, I don't see how to see. So I'm gonna intentionally get to the part that bothers me. I was kind of looking ahead. Okay, so then there's gonna be minus 2 times all of these. A2, A3, B2, B3, and then you're gonna have A3 squared, B2 squared. And then you can do that again for this next one. And again for the next one. So you're going to have a total of these 9 terms. Something that looks like this. Another one that has A1B3 squared. And another one that has A1B2 squared. With these 9 terms. And normally in the proof we square it and say, okay, let's write it without the square root and see how we can simplify. And then we'll work from there. Let's make my head a little smaller. Okay, is my window too small? It is too small. All right, let's fill in a little adjusting. Just a moment. Okay, so here's what I have. I pulled from one of my resources, and what one of the few places I've seen this worked out. One of the textbook I have here. So there's where we are so far. That's that expanded piece. I try as much as possible to make things non-mysterious. Now, since cross products are important to us, it makes sense that somebody was willing to go a little further and try to prove that this is connected to something else. Now, how they saw this next step, I am not sure. This is the same as this. I imagine this has some overlap with some discipline where these things come up. But this is a non-obvious factoring to me. If somebody forced me to prove this, at this point, I would cheat and I would then work from the other direction, meaning I would expand this out and expand that out. They're really big expansions. And then I would try to piece things together. I'm not completely surprised that this is happening because there's so much symmetry in the problem, but they regrouped. So I don't think I'm going to show that. I feel bad. I'm not actually getting, but I'm giving you the thinking. So I would do this times this, this times this, this times this. That's going to be, the main thing I see when I look up is that the A1, B1 squared is not in there. The other things are in there a bunch of times. And I would do the same thing with the next one. I see. And now maybe this makes sense to me. So if I expand this out, I'm going to have these extra terms, A1 squared, B1 squared, and then I have all the middle ones. And then this A1 squared, B1 squared is going to appear in the other one. It's going to cancel because the minus, it still doesn't fully prove it to me. So I'm a little unsatisfied with where I'm at. Maybe someone can point me to a resource where they show that algebra more cleanly. But that's one of these few places where I've never really done this. So I'm admitting defeat here slightly. That I've never actually worked out that those are the same. So that's, I guess it's good to admit that. I would expand this out. It would take probably 10, 15 minutes. I just see that I don't want to. Okay, this though is the magnitude of A squared, and this is the magnitude of B squared, and this is the dot product. So this was someone working hard to try to connect these pieces. So that's the only part. It's one of these particular bit of manipulations. I know there must be a cleaner explanation. I just have not seen it, and this is the explanation I have in our book. Okay, so at this point, what can we say? Now we can rely on the 10-star fact we have for dot products. So the rest of the proof I can show you. So let me get rid of this. Move this up a little bit. And then let's finish off this proof. So the way the proof would finish, so this is all saying this is equal to this. So this is the magnitude of A squared, the magnitude of B squared, minus, and then this is going to be the magnitude of A, the magnitude of B, cosine of theta, and that's all squared, 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 squared. And then a relatively nice thing happens. Here's what we get. We get this squared. We factor this out. And we get 1 minus cosine squared. And that's the same as sine squared. And the last little snippet is to take the square root of both sides. Now, a lot of students will say, don't you have to do plus or minus? Well, we know the length is a positive number. So these are all positive numbers. I don't know if sine or cosine is a positive number, except for the fact that I'm dealing with angles between 0 and pi. And for those angles, sine is positive. So I don't have to do the plus and minus because none of these values are positive. It's because we know the values. You do plus or minus in a situation where you don't know the values and you're trying to move from here and you're unsure whether it's the square root or the positive square root. But we do know something about the values and we know they're all positive. So that's it. It actually builds off of the dot product fact. And then, like I said, then we can interpret that as the area of a parallelogram. That does have some important consequences. In particular, if you want the area of a triangle in 3D, it's half of the area of the parallelogram. So it's pretty cool because it actually gives a general method for finding the area of a triangle in 3D. It says you just find two vectors that represent two of the sides, do the cross product, and you're done. Okay, hope that's interesting.